last time we defined renormalized Lagrangian, which is given by the classical Lagrangian plus the counter term Lagrangian. This second part has all the counter terms, which provide the counter term Feynman diagrams that cancel the divergences from the original from the Feynman diagrams of the original theory. So this part is divergent as epsilon goes to 0. Then the renormalized Green's function is given by a path integral over phi, where there are n phi's, but with a path integral measure given by e to the power minus integral of L renormalized. When we the L part of this Lagrangian density that will contribute to Feynman diagrams from the original theory, which have loops and divergences, and then counter term part of the Lagrangian will provide the counter term vertices, and that will cancel those divergences. So this quantity is finite as epsilon goes to 0. And we know that Green's function can be written as sum over 3 topologies of diagrams that are constructed out of the 2-point function, connected to 2-point function, exact Green's 2-point Green's function, and then 1 pi vertices. So this is written as G tilde 2, and these are written as gamma tilde n in momentum space for n greater than or equal to 3. And gamma tilde 2 for n equal to 2, gamma tilde 2 is nothing but G tilde 2 inverse. This is what we already know. And therefore, if all these Green's functions are connected Green's functions, these are connected Green's functions are all finite. All these gammas, gamma tildes, they are also proper vertices. They are also finite, and they are written in terms of m lambda mu. Mu appears in when we do dimensional regularization. This L includes mu and epsilon. And so this quantity is such, gamma tilde n is such that it is finite when we set epsilon to 0. So that is the physical limit. In addition to these parameters, they are also, it is also dependent on the finite ambiguities. And then the observables, the finite ambiguities that come in the counter terms, and then the observables is O is given in terms of the proper vertices, and therefore they are also, the observables are also written in terms of m lambda mu and these phi's. Now there are certain features of whatever has been told so far. One is that the couplings m and lambda, they run, which means that they depend on the mass parameter that was introduced for dimensional regularization. Then to make connection with physical observations, you set that arbitrary mass parameter to be at the physical energy scale associated to the particular observable that is being measured. So once you do that, then m of E and lambda of E are the values of the couplings at that particular energy level, which are unknown. They are theoretical quantities. They have to be measured, but you have to measure by writing the observable in terms of m E and lambda E, and then when we measure O, you get m E and lambda E from a few experiments, and then you use the same m E and lambda E to predict infinitely many other observables at the same energy level E. However, this process will not go through because of these ambiguities that are present, because nothing is predictable here, because there is an ambiguity sitting in. That ambiguity has to be fixed before measuring, before making connection between the parameter m mu and lambda mu with the observation. This fixing of FIs is called renormalization prescription. This procedure is equivalent to defining m and lambda in terms of gamma tilde 2 and gamma tilde 4, hence in terms of observables O. Now so once that is fixed, then this process, what I just described earlier, how to measure m and lambda with few experiments and then predict the results, predict observations at the same, many other observations at the same energy scale, that process goes through. But now, in order to have a complete picture of the entire thing that we are discussing, we need to understand the scale dependence of these couplings. So if we know the couplings at one scale, how do we know the couplings at another scale is one question that to be asked. But before that, one has to first understand why do they depend on the scale? Why are they dependent on the scale? So which is the first feature, let me explain why that happens. So couplings, more generally proper vertices, it is not only the two couplings. Couplings mean the proper vertices from the point of view of the effective action. But there are two independent couplings, m and lambda, but proper vertices also can be treated as can be viewed as coupling, as I said, from the effective action point of view. So they all run with mu. So the question is why? The reason is that we introduced bare quantities phi naught, m naught, lambda naught, and the bare vertices, and they are related to we had defined the bare quantities in previous lecture. They are related to the renormalized quantities phi, m, lambda, gamma tilde n, and mu. Okay, so these are called bare quantities, and these are renormalized quantities. These bare quantities are mu independent by definition. By definition, these bare quantities are mu independent, and therefore these relations allow one to see why these quantities are mu dependent. Okay, so this is the nature of these relations which I had explicitly written down in the previous lecture. So the nature of the above relations dictates that we must have m as m must depend on mu, lambda must depend on mu, and the proper vertices must depend on m, lambda, and therefore should have implicit dependence on mu through them and explicit dependence on mu. Note that it's not meaningful to say phi depends on mu, because phi is a theoretical construct that allows one to formulate what the proper vertices or Green's functions are. They are not directly observables. The observables are defined in terms of phi, but in our framework, the way phi appears, or the phi as a mathematical construct is used, is not observable. So since these quantities are related to these quantities, there must be, and these are mu independent, which means that there are combinations of these quantities which are mu independent. So let me write them down here. Lambda mu to the power epsilon times z lambda, which is given by mu to the power epsilon times lambda plus This I'm writing in MS scheme. Minimal subtraction scheme, which says that all this finite, which sets all the finite ambiguities to 0, and therefore all these equations that I'm writing on the right hand side, the right hand sides of these equations are all M independent. It is also a mass independent renormalization prescription, as discussed by 't Hooft and Weinberg. And I had explained the detail in the last lecture. Then m squared times zm square, where zm square is given by this quantity 1 plus sum over k equals 1 to infinity bk lambda over epsilon to the power k, and z phi to the minus n by 2 times gamma tilde n. The external momenta p, the set of external momenta, is represented by p, lambda mu, m mu, and mu. These are the combinations that are mu independent, and therefore if you apply mu times dd mu on them, then it must be 0. Let me specify the relation between these quantities z phi, zm square, and z lambda with the counter term a, b, and c, the way it was defined in the previous lecture. So z phi is equal to 1 plus a is equal to 1 plus sum over k to infinity ck lambda over epsilon to the k. Zm square equals 1 plus b z phi inverse, and z lambda is equal to 1 plus c times z phi to the minus 2. This is what we got, and from the counter term Lagrangian, from the original Feynman diagram calculations, one figures out what the counter terms are, where all these finite ambiguities are set to 0. That means counter terms are only the epsilon poles, and this is what we see here. A is basically coming from the counter term, which is basically the epsilon poles, and similarly, for zm square and z lambda, these are given in terms of b and c, and if you equate these expressions and these expressions with these ones, then that defines what ak and bk are in terms of when you read b and c, from there you can read out ak and bk, and from a one can read out ck. So these are only poles, and the residues are mass independent. So this is the structure that we got. Okay.